Concrete is literally the foundation of our world. It's everywhere. It's the most common man-made material on the entire planet. But what if I told you that our basic intuition, our gut feeling about what makes it strong, is just completely wrong? Let's crack this mystery wide open.
So what really makes concrete strong? It sounds like a super simple question, right? Probably has an obvious answer. But the real story is so much more fascinating, and it's all hidden away at a microscopic level.
I mean, it's just common sense, isn't it? If you want to build something tough, you start with the toughest possible ingredients. You'd fill your concrete mix with chunks of the hardest, most durable rock you could get your hands on. It just makes sense. But, as a group of scientists discovered, common sense isn't always the same as scientific fact.
Okay, check this out. This is the chart that basically kicked off a huge investigation and just baffled engineers. That yellow line? That's concrete made with a relatively soft limestone. And the red dots? That's concrete made with a really hard river gravel. And yet, the limestone concrete was consistently stronger. How could that possibly be?
And we're not talking about a small difference here. This was a result that just flew in the face of conventional wisdom. It was a genuine scientific puzzle that absolutely had to be solved.
So, the National Institute of Standards and Technology, or NIST, they teamed up with the Federal Highway Administration to crack this case. They decided they were going to put this whole puzzle under the microscope. I mean, literally, to figure out what on earth was going on.
The first step in any good mystery is to identify your suspects. And in the world of concrete, the rocks and gravel that get mixed into the cement are called aggregates. And these guys were about to become the focus of this entire investigation.
And this was a serious nationwide search. They didn't just test rocks from one little spot. Oh no, they gathered 11 completely distinct types of aggregate from quarries all over the country to make sure their results were rock solid.
And wow, what a lineup it was. They had everything. You've got your hard hitters like diabase and granite, then you've got softer stuff like limestone and even marble. It was like a geological battle royale, all designed to see which one would create the champion concrete.
And it wasn't just about what the rock was made of. It was also about its shape. The diabase, for instance, was all sharp and jagged. But that silicious gravel, remember the one that performed so poorly? It was smooth and rounded. Could that be a clue?
To find the real answer, the team at NIST knew they had to go deeper, way deeper than what the naked eye could see. They had to take a journey into the inner world of the concrete itself. And let me tell you, this was a painstaking process. They take these big cylinders of finished concrete, slice them into thin discs, set those discs in epoxy, and then carefully grind and polish them down until they were so thin that light could actually pass right through them. And when they put these samples under a special polarized light microscope, wow, the rocks revealed these absolutely stunning complex internal structures. Each one had its own unique mineral fingerprint, like this gorgeous granite on the left and the sandstone on the right. The scientists measured everything they could possibly think of. The rock's own internal strength, its shape, its surface roughness, how stiff it was, and even something called surface energy, which is basically its chemical stickiness. They were on the hunt for any property, anything at all, that would predict its performance in concrete. So, after all this testing, after all the grinding and polishing and measuring, the clues finally started to point to a single really surprising answer. And here it is. This is the smoking gun, right here in the data. The concrete made with tough stuff like diabase and granite, they reached strengths over 52 megapascals. But the concrete made with that really hard silicious gravel, it was the weakest of them all by a long shot at just under 38 megapascals. The strength of the rock itself was clearly not the deciding factor. It turns out the answer wasn't in the rock, it was in the connection to the rock. Scientists zeroed in on this thing called the interfacial transition zone, or the ITZ. It's this incredibly thin layer, we're talking thinner than a human hair, where the cement paste actually bonds to the surface of the aggregate. This image from an electron microscope shows you that exact zone. The big solid mass at the bottom, that's the aggregate. The stuff on top is the cement paste. And that tiny little boundary between them, the ITZ, that is the single most important factor. The quality of that bond, that's everything. And hey, you don't have to take my word for it. The researchers said it best themselves in their final report. The strength of the rock, well, it isn't always the whole story. What really matters is how well the cement can grab onto it.
This discovery just completely flipped our understanding on its head. We went from this old assumption that stronger rock equals stronger concrete to a brand new, much more accurate one. The best bond makes the strongest concrete.
And that finally explains our original mystery. That super hard gravel was just too smooth and chemically passive. The cement paste couldn't get a good grip on it. It was kind of like a weak, slippery handshake. But the softer limestone? It had a rougher texture and a more reactive surface, creating this powerful chemical and physical bond. Now that is a handshake with incredible strength.
So, okay, this is a really cool microscopic discovery, but why does it matter in our big macroscopic world? Well, the implications are actually huge.
Well, for one, understanding the secret of this bond lets us design stronger, more durable concrete, and that means safer bridges and taller buildings. It also means we can get the same strength with less material, which lowers costs and, this is a big one, reduces the huge CO2 footprint of cement production. It even means we can be way smarter about using local rock resources that we might have overlooked before.
So in the end, the secret to strength was never really in the rock itself, but in the handshake between the materials. It's just a powerful reminder that there are these amazing scientific principles waiting to be discovered in the most common things we see every day. Principles that can help us build a better, safer world. It really makes you wonder, what else are we overlooking?